And then we can switch to Justin's talk if you want to share your screen, Justin.
Yeah, hi. Can you see my screen?
Yes.
Okay.
You may want to put it on full screen.
Yeah. Okay, so I'm gonna talk about our recent.
Let me introduce you.
Oh, sorry.
Okay, so for the last talk of this workshop, before the discussion, we'll have Justinas Rumbutis, who will be talking about double copy relations in massive theories. Go ahead.
Okay, so I'm gonna talk a bit on our recent work at Imperial College London with Arsha Mameni, Andrew Tully, and Mariana Carrillo Gonzalez. So we saw in this conference that double copy between Yang-Mills and general relativity can be really useful tool in simplifying gravitational wave calculations. And this relation between Yang-Mills and GR is the most studied one. However, people have found other theories related by the same double copy, the same relation. For example, nonlinear sigma model and special Galilean and many more. So it is natural to ask what makes these theories special and how general is double copy? What are all the theories that we can relate by it? And what we've been looking in particularly possible relations between massive spin 1 theories and massive spin 2 theories. So if such relations existed, maybe they could simplify some calculations in massive gravity, for example, calculating gravitational waves or black holes, or understanding Einstein screening mechanism more analytically. And over the past few years, there's also been quite a lot of related work on double copy with massive matter. So in those cases, the amplitudes have some massive external states, but the force is still mediated by massless gluons and gravitons. So what we started with was massive Yang-Mills theory. Its action is given here. And we checked whether it's related to DRGT massive gravity theory. So the action is given here. And in this action, we have two free coefficients. So two of these kappas are free. So both of these massive theories are actually effective field theories, which means that they only make sense up to a particular energy scale called the cutoff. And for massive Yang-Mills, it's given by this ratio of the mass and the coupling, which you can think of if we get this massive Yang-Mills from gauge theory with Higgs field. By integrating out the Higgs field, this is basically the order of mass of the Higgs. While for massive gravity, the cutoff is this lambda 3 given by the combination of graviton mass and the Planck constant, but it is not known whether there is some sort of Higgs mechanism for massive gravity. And if we just focus what happens for these theories close to the cutoff, so in the high energy limit in which these effective field theories are still valid, they simplified quite a lot because some of the degrees of freedom decouple, and this is known as decoupling limit. So if we look at the decoupling limits of these two massive theories, we see that there is an argument which suggests that these theories could be related by double copy because the decoupling limits are actually related by double copy. So if we take the decoupling limit of massive Yang-Mills, we get a nonlinear sigma model. And if we take the decoupling limit of massive gravity, we get a Galilean theory, which is a scalar theory, which we already saw in several of the talks in this conference. And one particular type of Galilean called special Galilean is actually a double copy of nonlinear sigma model. So this suggests that there could be some relation between these two massive theories. So we started by looking at the number of degrees of freedom in both of these theories. So for that, we had to decompose the product of massive spin 1 field, of two copies of massive spin 1 fields in terms of irreducible representations of the massive little group. So we get a massive spin 2 field, H, massive 2-form field, B, which in 4 dimension describes particle of spin 1. Which is different from massless keys, and massive scalar phi. And the next step was to look at the 3-point amplitudes, and we found that for a massive Yang-Mills, the 3-point on-shell amplitude looks the same as in the massless case if we express it in terms of polarizations and momenta. While for massive gravity, only this first line is the same as GR 3-point vertex. So basically, this first line is already Yang-Mills squared. But there's an extra piece, and if we want the double copy to work, we need to make sure that this extra piece is 0. So we need to fix one of these two free coefficients, this kappa 3, to be -1, such that the double copy works at 3-point amplitude level. Then the next thing was to look at 4-point amplitudes, and then we wrote the massive Yang-Mills 4-point amplitude in this usual form, where C's are color factors and N's are kinematic factors. And we found that kinematic factors obtained directly from Feynman rules already satisfy the color kinematics duality. So this Jacobi identity is 0. And that means that we can directly square them using double copy formula to get gravitational amplitude. And for example, when we constructed the pure massive graviton scattering 4-point amplitude, we found that we can interpret this double copy answer as 2 terms. So the first term, this first line basically represents an exchange of massive graviton. So it's just an exchange of massive graviton where both of these free couplings in the action are fixed to be of these values. And then the second line, the second term, represents the exchange of massive scalar, because we already saw that we have a massive scalar in this theory. But this is just graviton amplitude. We also have to consider all the possible other scattering processes. So remember that we had 3 fields with 3 different spins in the double copy of massive Yang-Mills. So this is represented by this J. So J is the spin of the external state. So basically it represents either H or B or phi on each external leg, and lambda is the helicity of the state. So to construct all the possible processes like this, we had to combine the 2 copies of massive Yang-Mills numerators with Klebsch-Gorlin coefficients. And once we constructed all the processes, we constructed an action which would match all these amplitudes at 3 and 4-point level. And it's given by this long expression. This action has lambda 3 cutoff as expected for massive gravity theory. And then we try to take the decoupling limit of this action. And what we found that it doesn't give a special Galilean as expected, but rather this bi-Galilean theory coupled to spin 2. And this means that double copy and decoupling limit, these two operations do not commute, because if we first took the decoupling limit of a massive Yang-Mills, we would have obtained a nonlinear sigma model, and the double copy of nonlinear sigma model is a special Galilean, but this is not a special Galilean. So then we try to understand why this, why these two operations do not commute, and the reason for that is actually color kinematics duality. So these ends that satisfy color kinematics that we calculated from Feynman rules, they actually contain a piece, this sigma, which is infinite in the decoupling limit, because it has 1 over m cubed, and in the decoupling limit only terms with 1 over m squared are finite. But of course, this sigma must cancel out in the massive Yang-Mills amplitude. And of course, it does by this Jacobi identity on the color factors. So really, this sigma, it does not contribute to massive Yang-Mills amplitude. But when we do double copy, we need to keep it for the color kinematics duality. So in the double copy answer, in the end, this sigma piece gives us this term, which is suppressed by lambda 3, the cutoff of gravity, massive gravity. So it is finite in the decoupling limit of massive gravity. But it is responsible for the non-commutativity of decoupling limit and the double copy, because if we start with massive Yang-Mills, we take the decoupling limit, we must cancel out the sigma because it's infinite in the decoupling limit. So we use the Jacobi identity to cancel it out. We get nonlinear sigma model, and if we double copy it, we get the special Galilean. But if we first do the double copy of massive Yang-Mills, we keep the sigma term for color kinematics duality. We get this massive gravity action with extra fields, and the decoupling limit of that is bi-Galilean theory. So this sigma survives, and it is actually the difference between special Galilean amplitudes and these bi-Galilean amplitudes is actually encoded in this sigma term. So then if we go further to 5-point amplitudes, we encounter a problem, because at 5-point there are spurious poles in double copy of massive Yang-Mills. So actually we cannot even interpret the double copy of massive Yang-Mills 5-point amplitude as some amplitude coming from a local physical theory. And this was first found by this group. And to understand the origin of these spurious poles, I'm gonna now explain this double copy procedure for n-point amplitudes in this matrix form. So we can write the n-point gauge theory amplitude in this form, where G is the coupling, C is the vector with color factors, D is a diagonal matrix with all the propagators, and N is a vector with kinematic factors. Then we can write the Jacobi identity in this matrix form as some matrix M acting on color factors is 0, and the number of non-zero rows in M is going to be equal to the number of Jacobi identities. And for color kinematics duality, we need the same equation for kinematic factors. And once we find these kinematic factors satisfying it, we can just replace C with N and get the double copy amplitude. So if we calculate descent directly from Feynman rules, then they are gonna be local without any poles, but they may not satisfy the Jacobi identities, the color kinematics duality. So for that, we need to shift them, but this shift cannot change the amplitude, because it's this shift, it's like a gauge transformation or a field redefinition. So in order for the amplitude to be unchanged, we need to choose this delta n to be of this form, because if it's of this form, then if we substitute it back to the gauge theory amplitude, the delta n cancels because we have some factor like MC transpose, which is 0 by the Jacobi identity. So if we choose it to be of this form and impose the color kinematics duality on the shifted ends, we end up with this matrix equation, this equation 4 that we need to solve. So the V is the vector that we need to find. And this matrix that we need to invert, M transpose, it's gonna have a non-zero block matrix. We call it A, and this is the equation that this is the solution for V basically that we have, where U is basically the violations of all the Jacobi identities, this Mn. Then we can substitute the solution back to the expression for double copy, and by doing after doing some algebra, we are just left with two terms. The first term doesn't have any problems. It doesn't have any spurious poles because D only contains physical poles from gauge theory amplitude. But the second term, this might be problematic because matrix A in general, its elements are polynomials in Mendel sums. And of course, if we do inverse of that matrix, in general, we're going to have some polynomials in the denominator, which would be spurious poles. And the denominator of a matrix is actually coming from its determinant. So really, these spurious poles are coming from the determinant of A. And for example, in 5-point massive Yang-Mills, the determinant of A is this expression. So this product of these contains all of the physical poles, but this polynomial P is this huge polynomial here in Malnussen variables that is, of course, a spurious pole, because we cannot have anything like that in the denominator of physical amplitude from a local theory. So then we can think what happens in some cases for which we know double copy works for any endpoint amplitudes, for example, in massless Yang-Mills. And we find that in that case, A is actually a singular matrix. So if we want to invert it, we can only do it in the subspace orthogonal to all the null vectors of A. So we require U to be in that subspace. In other words, U to be orthogonal to the null space of A if we want to be able to invert A. So for massless Yang-Mills, this requirement is equivalent to the BCJ relations. And in 5-point scattering, matrix A is 9 by 9 matrix, which only has rank 5. So there are 4 null eigenvectors, or 4 BCJ relations. And in the 5-dimensional subspace orthogonal to all these null vectors, its inverse is quite simple and it doesn't give any spurious poles. Then we can copy everything what happens in massless case to a massive case, but with some more general spectrum, not just a single mass. And we can require that the propagators in massive theory would satisfy exact same algebraic relations and as the massless propagators. And the simplest example, of course, is 4-point. So you know that in 4-point, the propagators, the massless propagators STU add up to 0, but in the massive case, that's in general not true. However, if we choose these exchanged masses very carefully, this M12, M13, and M14, we can tune them such that these massive propagators also add up to 0. So we can construct some massive theory in which A would have exactly the same rank as in the massless case. And these constraints are called spectral conditions. They were derived by this group. So even if we construct a massive theory with a spectrum satisfying these constraints, we would still need to check that the interactions satisfy the BCG relations. Otherwise, we cannot satisfy color kinematics duality. And one example of theories satisfying the spectral conditions are Kaluza-Klein theories. And of course, the massive propagators must satisfy the same relations in that case, because really they just come from massless propagators in higher dimension. So what we try to do, we try to consider this Yang-Mills theory with higher dimensional, higher derivative operators in 5 dimensions, which are known to satisfy color kinematics duality. But then we try to compactify it back down to 4 dimensions. And rather than keeping all the couplings the same as we get from doing this process, we just change all the couplings to have arbitrary values, and to see if we can, by imposing BCG relation, we can have something other than KK. So some new massive theory which would satisfy the color kinematics duality. So the action for this looked like this huge action with a lot of operators. So there seems to be a lot of freedom in satisfying BCG relations, because each of this term has a different arbitrary coupling. So there seems to be a lot of freedom. And we calculated the 4-point amplitudes. They were given by these kind of diagrams. So we considered all possible different external masses on external states. There's also a massless scalar in the spectrum of this theory. And we also considered 5-point amplitudes, and the diagrams for them look like these. And these, for example, 4-point amplitudes have this kind of form. So we have a lot of vertices with arbitrary coefficients, both 3-point and 4-point. And from BCG relation, we get this kind of constraint. So the products of these two couplings have to be related. But if we just look at one single scattering process, there seems to be a lot of freedom, because we can scale this G12 by something, and then G34 by the inverse of that, and this would still be satisfied. However, when we combine all the 4-point scattering processes, we find that the BCG relations eliminate almost all of the freedom. So almost all of these coefficients of all of these operators contributing to 4-point amplitudes are already fixed, except for one, this G0SS. But if we also impose the 5-point BCG relations, we find that this free coefficient at 4-point is fixed, as well as all the free coefficients of 5-point operators, the operators contributing to 5-point. So at 3 and 4-point scattering amplitudes, we cannot have any freedom. The only way to satisfy BCG relations is the original Kaluza-Klein theory, which suggests that these constraints and these spectral conditions, they are very strong, and probably maybe this way of doing double copy is too restrictive, because it seems that the only thing we can get it is either if we just copy whatever happens for massless case, then what we get is either a massless case or Kaluza-Klein of a massless case. So now we are looking more closely at the spurious ball and massive Yang-Mills 5-point amplitude, which actually has some structure. It can be expressed as the Gram determinant of 4 out of 5 of these external momenta, of the external states. And this Gram determinant is not only non-zero if the dimension of the spacetime is greater than 3. So that brings me to the direction for our future work. So we're gonna continue looking for other massive spin-1 theories compatible with color kinematics that do not give any spurious pole in double copy. And we're gonna try to understand whether we really need to require the rank of A to be the same in massive case as in massless case. And also, as I mentioned, we're gonna look at the lower space-time dimensions. Okay, that's it. Thank you for your attention.
Okay, thank you very much for this nice talk. We have time for some questions. Either was very clear or, yeah, Dana?
Yeah, so I just have a little question. Thanks for the nice talk. Yeah, it's sort of interesting story about this, this 5-point thing where, you got this spurious pole and stuff's not working out. Just trying to make sure I'm understanding what's going on. Life is usually very good if you can have a double copy, where the numerators are all local. So obviously that's not what's happening in this case. You've got poles sitting around the place. Do you know, have you been able to rule out the possibility of a local double copy?
So one of the possibility of this could work with for a very specific theory, even if this spurious poles is there, maybe the interactions are very special and they actually cancel out this spurious pole. That's one of the possibility that would give something that could work as a local double copy, but we are still investigating. We are still looking for these kind of theories.
But you mean, but then in for a generic case, that you cannot possibly find a set of numerators so that there's a local double copy.
Yeah, so it seems that in massive case, at least in the case of just a single mass, in general, the local double copy really doesn't work. We just if it works, we just really have to tune these interactions. Yeah.
Maybe just another thing, just on this topic. I mean, as I'm understanding, and maybe I'm not quite understanding correctly, but I'm understanding that the massive Yang-Mills series you've obtained by something like the Higgs mechanism.
Yeah, so we basically
and you've integrated out the Higgs, right? So the Higgs is at some. So you've removed some.
So we can get this this action here. Like we can get this action by integrating out the Higgs field in the where the symmetry breaking mechanism such that all the gauge bosons get the same mass. But of course, we're going to have extra operators suppressed by the cutoff scale. So we just
I guess that's what I was asking, right? So, or sort of getting at. So this is an effective theory, it has a cutoff.
Yeah.
And the poles you're seeing, are they within the domain of validity of the effective theory or outside it?
Yeah. I mean, the spurious pole that we get. It's really not suppressed by any power of the cutoff. So it seems, that it is in the validity of the effective field theory. Yeah, so here we just have mass and minus some variables.
I guess that's right. So there's certainly no reason why I'd see a scale separation. You just have this random cut. Okay. Yeah. Thanks.
It's probably worth saying, just following up on that in a sense it's because there is no Higgs version of massive gravity, one could have expected this, because if there had been one, it would have matched up and been consistent. And it's sort of the absence of that that's the problem.
Yeah, that makes a lot of sense. So in a way, I mean, if it's how it works, you'd have to work harder to find something that wasn't going to work. And presumably there's some reason why it's hard to find a, I mean, if you were able to, yeah. I mean, if you were able to find a double copy construction of this thing that was just working, presumably you would be able to take the regulators away, right? You'd have a, you'd find a UV completion for the mass of gravity, and I guess that's the point you're making, isn't it? Yeah.
So, for example, you might think, you know, in the case of DGP model where you can give the graviton an effective mass, but ultimately the theory is still diffeomorphism invariant and it's still massless gravity in 5D. Perhaps it might be more promising for that to work because ultimately it is still a diff-invariant massless theory. But nobody's done that. That's so horrendously complicated.
I mean, then you would want to understand how to write your double copy in such a way that you have your brane, you have your boundary conditions. I guess that's where the complication lies, no?
Yeah, that's right. I mean, obviously the bulk works because you've just got bulk 5D Yang-Mills and bulk 5D gravity, but then you've got boundary terms. So I don't know how much people thought about the implication of the double copy for boundary terms in such a setup. It's yeah, no idea.
Yeah, I mean, it's one thing to have your double copy for gravity, but you need to have your double copy for the extrinsic curvature, which is not something that you would get typically, right?
Right, but I'm allowed to put Yang-Mills with a boundary, right? So, and then if I naively do that, what would I get? I guess that's the question.
Yeah, I mean, I think you'd expect some of the boundary conditions would map. You know, that there should be some, you know, simple boundary conditions say from Yang-Mills series should map to something sensible in gravity, but it's not clear that any boundary condition in gravity is going to be constructible from some simple thing, a single copy in Yang-Mills.
So we have time for more questions.
Yeah, maybe just a comment. There's because it's not directly related, obviously. There is yet a theory that kind of has a wall sheet model for it, which is not a good theory. It's not unitary, etc. But it has a bunch of it has two massive spin 2 states in there and a massless graviton, and kind of an analog in terms of a massive type gauge theory with also a possibly a unitarity problem or something that's been looked into in the context of this ambi-twister type constructions. I'm just commenting that this thing exists, and actually maybe even Oliver Schlotterer and the others worked out the double copy between those two things. You guys might actually know the answer to this, but yeah, I'm just commenting on the existence of that thing.
So it has a spectrum with a massless mode and several massive modes?
Yeah, so it's not really a massive gravity, I suppose, in that sense. It has gravity plus 2 extra spin 2 massive states, one of them being a tachyon. So, but, yeah.
That's interesting. Yeah.
And since, sorry, the comment is that since this thing is a wall sheet thing, it most likely has a double copy between those two.
Right. Mm-hmm.
Any other question or comment?
I might make another remark if that's okay. Have you looked into things like ghosts. I mean, often ghosts are quite convenient in the double copy. For example, I mean, if you want to cook up something that looks just like general relativity, pure general relativity, the double copy wants to give you kilotons and other nonsense, axions. No, maybe they're not nonsense, but those come along. So sometimes it's useful to introduce some other stuff in the theory, treat it as a ghost and give it some quantum number so it can't, so it just has to double copy against itself somehow. I mean, I guess Henrik Johansson and Alex Ocharov, for example, have used this for looking at making loops in general relativity from the double copy. So I'm just curious whether you've looked into states like that. Maybe they could help remove these funny poles.
So as far as I know, this technique with ghosts is used to like remove the extra field in the axial dilaton gravity, right, to get just pure GR. But in our case, I mean, we really have a problem on the gauge theory side, not really on. We can't even go to the gravity side at 5-point level yet. So, yeah, maybe adding, that's something that we thought, maybe adding extra degrees of freedom.
Yeah, maybe, I'm not sure that, necessarily needs to be ghosts or anything like that. I guess so, I mean, you have this example where there was a parameter fixed, like your kappa 3 minus 1 had to be 0 or something like that, And that would seem to be something where you could say, okay, well, maybe if I add some extra degree of freedom in the Yang-Mills and give it some reason why it just double copies against itself, it can potentially, well, maybe you have to think about it, but it could potentially get involved in relaxing some constraints like that. I mean, the pole you're seeing is a more intricate thing, I suppose, but, I mean, it's not just that you have to double copy some set of massive Yang-Mills fields and expect to get, some set of massive gravity fields. I mean, maybe there's some more general thing that you're supposed to double copy, or maybe you can, but I mean, it'd be very interesting to have sort of a good theory that just doesn't have a double copy.
Yeah, that's something that we thought about. Maybe the spurious pole can be removed by adding extra degrees of freedom and higher operators, but the thing is we still need to make it such that the 4-point remains as it is, because we might easily mess that up. So yeah, it's not clear actually how.
If I might add a couple of comments here, there is of course the possibility to add extra degrees of freedom while messing up the 4 points. Of course, if you add back the Higgs that has been integrated out, and everything becomes nice and color kinematics goes fine, and you can double copy things just as we always do. But it's not these degrees of freedom that need to be added to keep the 4-point as it is for massive gravity, but something else.
I mean, you could imagine adding something that just has 5-point interactions or something, right? I mean, why not?
You could.
You said like you love that idea.
I guess, I mean, these extra poles seem really strange. So a single 4-point interaction seems to me unlikely to fix it, but I don't know. So.
Well, maybe another comment, if I may. Do you hear me?
Yeah.
Yeah. So just to make sure that you really want all your vectors to be massive, as far as I understand, right? Because there's also just the possibility, I think, that you can add massless vector bosons, and then you will have a nicely massless poles, and that part for sure will double copy, because I guess that will be a KK kind of. But so you're specifically interested in things that are not Kaluza-Klein related.
Yeah, we were trying to find something which is not Kaluza-Klein, but
right, and that would also be yeah, that will also double copy into gravity that has a normal massless graviton. So
Yeah.
really don't want that, I guess. You really want to have some single copy of your massive gravity.
Yeah, we're trying to understand whether such things even exist. Like, is it just Kaluza-Klein theories, or is it something like?
Yeah, because I normally think of massive fields as matter. So, and the double copy comes from the massless part, and it works out in presence of matter. But you really want to do it without the massless part. And yeah. I was always expecting something like that. And as soon as you showed s minus m squared, t minus m squared, and u minus m squared in the poles, then I mean they don't sum up to 0. So you had to have some problem, and yeah, I guess you did. So well, it's interesting that you can really pin down things to the Kaluza-Klein type theories in this setting, at least. It's very interesting. Thanks.
Could I ask one more question?
Yes, go ahead.
So I was wondering, you might have said it and I missed it. If you actually try to sit on these additional spurious poles, is there some nice value of some invariant that at that pole, or is it just a solution to some random looking equation?
Well, yeah, I mentioned in the last slide that this pole actually is not, it has a pretty simple structure. It can be written in as this Graham determinant of 4 out of 5 of the moment of external state. So yeah, definitely it is possible to choose the kinematics such that this pole goes like on shell, I guess, or
Okay, thanks.
Okay, so I think now is a good time to thank Justin again.